Started. Hi, everybody. My name is Caitlin. I work at Central Library, and today for our Tech Talk, we have a web developer. His name is Yahya Lazrak, and he's here to talk about machine learning, kind of give us an introduction to the basics. So I will go ahead and pass it off to him.
Okay, thank you very much. Hi, everybody. So yeah, today I'm gonna do a kind of short talk about basics of machine learning. First, about me. My name is Yahya Lazrak. I'm a full stack engineer at Airflow. That's a new startup here in town. Just joined less than a month ago. And then I'm also a machine learning enthusiast, as you can tell from my talk. So quick definition for machine learning is basically any algorithm that can improve itself by itself. So it does not need any explicit instructions. All it needs is basically a lot of data, and then you can figure out what needs to do. So there are, like, if we can talk about the types of machine learning. So there's two main categories. There is what some people call shallow learning, or traditional learning, and there is a new category that's got very exciting in the last few years called deep learning, which most of the advances that happened are in the deep learning category. But since we are talking about the basics, we're gonna talk more about the shallow learning, just to get the basics. And for both of them, there is supervised learning. That's basically when you tell the algorithm, you give it the data, and you tell it example of this data, what results does it give us, and then from that it learns. So next time it sees some new data, it will determine what's the output should be. There is also unsupervised learning, which basically we don't know what the result should be. We just give the computer a lot of data, and we say, hey, tell us what things you can deduce from this data. So, and then for supervised learning, there is regression. That's when the result is continuous. Let's say, for example, try to predict house prices. So it's a continuous, number. There is also classification. That's when the results are categorical, like if it's true or false, or if we want to see if this picture is a cat or a dog or a horse, something like that. So that's called the classification. And then for unsupervised learning, there is something called clustering. Basically, we're just trying to put the data into different groups. And there is anomaly detection. That's let's say something like if you try to detect fraud or something like that. We know what good results are, but we don't know actually what things that are not good. We just say, okay, this is normal. If anything, outside of this normal area, then we'll say it's abnormal. Yeah, and then of course there is, as I said, there's deep learning, which is it can be like all the other ones, but mostly is for supervised learning, and uses artificial neural networks. Okay, so for regression, we'll start with linear regression. As I said, that's when the output is a continuous function. So basically, we have a bunch of data. Let's just think of this graph, you have dots, and then we'll try to fit a line through this data, like trying to predict the house prices or stock market, something like that. So in the case of house prices, let's say, for example, we have data about square footage of a house, and then the price that the house was sold. So we present that in a graph, and then we'll try to find the best line that will fit this data. So first, we'll just draw any line like this, and that's clearly it's not very good. But the nice thing about algorithm is it's gonna try to improve itself. So it's gonna move the line a little bit, and is that better? So every time we move the line, we calculate the difference between what the value would be if it was in the line and then the actual value, and then we keep moving the line until we try to get it as close as possible. And it doesn't have to be a straight line. It can be also a curved line. And then we try to get the best result, and we know that's done correctly. And then for classifications, like, as I said, that's when like you have categorical output. Like, we want to see if somebody is sick or not, or like you have a bunch of pictures of animals. You want to know what animal is that. So there are kind of like different algorithms. So first one is logistic regression, which, as you saw earlier, regression means basically try to fit a line. But if I try to fit a line through this, so let's say, for example, this is like try to see if somebody is sick or not. Like, let's say this is blood pressure, and here whether somebody has a heart disease or not. So as the blood pressure goes up, like these people are fine, but then people who have like really high blood pressure, for example, these are just examples, you know, are sick. So if you try to fit a line, of course, that doesn't work very well. But there are like all kinds of stuff. It can be curved lines. So there is this kind of function called sigmoid function, and sigmoid just means that is the shape of an S, and that tries to, you know, that kind of gives you a good result. And sigmoid function is always between 0 and 1. It can never be more than 1 or less than 0. And then you can use the number as like a percentage. Like if you, for example, you say you find the number is 0.9, you say, oh, I'm 90% confident that person is sick, something like that. A different algorithm is called support vector machine. And here, again, like we have, you know, a bunch of data, and instead of trying to find a line that will fit the data, we'll try to find a line that separates the data. So let's say, for example, here again, we have like this here we have a blood pressure, and here maybe oxygen saturation or something like that. So try to find the line where like that's kind of makes clear separate the data. So again, like we move it until we find the best separation, and that will be the maximum distance between each kind of data and the line. And of course, it's not going to be perfect. Like you can have some patients that are on the other side. So this is all just statistical calculation. So you always have some kind of error. And another algorithm is called decision tree. And yeah, to say, for example, like in the case of like, let's say heart disease, like we have all kinds of parameters, and then we figure out what's the most important one. Let's say, for example, it was age. Like if the age is greater than 60, then, you know, if yes, then look at the gender. No, look at chest pain. And then, for example, you know, if like when looking at gender, if it was like male, then look at the weight and stuff, and then you find, well, like whether that person is sick or not sick, for example. And that's you know, that's kind of simple, easy to understand, but the problem is, with this, it doesn't generalize very well when you have because let's say you don't have some of the information, or just like it's very specific to just like the data you train on. When one as soon as you see something new that never seen before, most of the time doesn't know it very well. So there is a trick what they do, and well, yeah. So those are the advantages and drawbacks. So it's simple and easy to understand. And something called like overfitting, which is basically it knows very well the data that you give it, but then once you see something new, it doesn't know, actually, it predicts very well. So there is another thing called the random forest, and basically it takes that data and randomly removes some of those data points, and then try to make a decision tree for that, and then do it again, like take the same data, randomly remove some other features, and then do another decision tree, and then you do a lot of them, and then you combine all of them, and then it gives you, that's what's called the random forest. So you have a lot of them, and that gives you a much better prediction. Now for the unsupervised learning. First of all, like I don't know if do you guys have any questions or something before? Like I don't want to like go like really quickly and.
I haven't seen any questions in the chat quite yet.
All right, cool. All right, and if I'm going too fast, feel free to slow me down. I'll just. So now for like the unsupervised learning. So this is always like you tell the computer, here is information, the expected input, the input here is the expected output, learn from that. Sometimes we just was like, we have all this data, I wanna try to get some information from it. So one of them is like clustering. Like you can think of, for example, Google News, right? Like you see news article, and then below that you find like other, this kind of similar news, but from other news sources, like right there. You don't want to find like a whole page of the same subject. Or like if you want to take something simpler, just like market segmentation. So like people have like all kind of sizes, but usually when you want to make a t-shirt, you just want like small, large, and medium. You cannot have like all. So you take people's sizes, and it was like try to group all these sizes in like 3 different ones or something, or 4 or 5. So how do we do that? So let's assume, and this is kind of like clear cut, we have like data like this, and we want to split into 2 groups. Of course, computer, I mean, for us, it's easy like this, but computers doesn't know very easy. So what we do, we just take 2 dots and we put them randomly. And then we take all the dots that are closer to this blue one, and then color them in blue, and then the ones that are closer to the red one, color them in red. So like that. And then we take the average of all the blue ones and move that center to that location, and then the ones that are in red, and move it, took the average and move it there. So it become like that, and then repeat again the same process. So it's like find all the dots that are closer to the blue center and color them blue, and then the ones close to the red one and color them red. So it becomes like that, and then move it to the center again, and then you keep doing it over and over, and then you have 2 groups. And again, like this looks easy when you have just 2 dimensions, but usually when machine learning, you have like, sometimes hundreds of dimensions, and yeah. So this is all just for simplicity. And then another one is anomaly detection. So basically we use statistical variance to see if something is within normal criteria or not. And that's used a lot for like fraud detections, trying to see like if there are any manufacturing defects, or like like data centers. Like sometimes you don't want to wait until those servers like completely crash and you lose all the data. It would be nice if you know before. So how do we do that? And again, with 2 dimensions, we have data like this, and we can see the thing with anomaly detection is like we know that the majority of what we have is normal. So we look at this data and we try to find like what's the standard deviation between most of the dots, and then it's basically this area. So anything that is outside of that, that will be abnormal. And then there is the newest well, it's probably pretty old, but like all the most new advances are in artificial neural networks, and especially deep learning. And that's basically it's I guess we're trying to see how the brain works, and it's not really that way, but anyway. So we have in the brain, we have the neurons that are connected to each other. So we try to kind of emulate that with the structure of those artificial neural networks. So how does it look like? So basically it's like that. First you have an input layer, that's the data that we know. There's an output layer, that's basically the result we want. And there are like hidden layer, like here just one for simplicity, but it can be any number of hidden layers. So like here you can like the input layer can be like customer age, debt ratio, monthly income, stuff like that. And then like basically each one you give it some weight, and then those weights, like this one is gonna take this x1 times w1 plus x2 times w2 plus x3 times w3 and add them all together. And then there is a function here that basically is called activation function, that if it's above some threshold, it's gonna give you a result. If it's lower, there are different cases. It can be either just 0 or it can be negative, and so forth. So that's how you get like H1, and then similar thing to get H2, and you might have other weights, other hidden layers. So you go from hidden layer 1 to hidden layer 2 and 3 and so forth, and then you get to the output. And then how does it learn? so there's this thing called, they call it back propagation. So once you get to the last layer, then you can compare it to the actual result. And you're like, is that correct or not? And if it's far, then goes backwards like this one goes back to, well, let me show you, so it's kind of like this. So this is with like a lot of networks, a lot of hidden layers. So once you get to this, for example, price, it was like, well, the price was far off. So go back to this and correct those weights here. And then after those are corrected, it will go again backwards, like you need to correct the weights, and it keeps going back all the way to get here. And then you run it again all the way from start to finish. And then you see, you know, how far you are. And then you go back, you keep going back and forth and until you get like the closest possible to the right number. And those, like, now you have a trained model, and then basically it just becomes one way to find to find the price you're looking for. So why is the artificial neural networks is doing so well recently? So basically, there's this graph that shows like how they compare with each other. So like the traditional machine learning algorithms, like the ones I talked about earlier, they kind of do, and so this is the model performance, like how well they do compared to how much data you have. So those ones, they do pretty well, but at some point, you can keep giving it as much data as you want, like they don't improve as much, like they kind of plateau. And those small, medium, and large is just basically how many hidden layers you have. So you can see that the more hidden layers you have, you can give it more and more data, and it will keep improving. And that's basically how like Google and all those big companies get really good machine learning algorithms, just because they have a lot of compute power and they put like massive amount of hidden layers, and they just keep improving it and feed it a lot of data. Yeah. So again, I mean, I went pretty quick here. I'll try to leave more time for questions if you guys have any. But just in conclusion, like again, so like there's supervised and unsupervised learning. Supervised just means basically we know beforehand, like we train the model on the data and the results that needs to like the result, and then it will learn from that, and then later when you give it like new data that doesn't have any results, it will tell you, oh, okay, here's what the result should be. And in unsupervised learning, we just give it data, like give us some insights from that. And then there is regression. That's when the result is continuous. But classification, when the result is categorical, like animal pictures or just like true or false. And then, yeah, for unsupervised learning, there was like clustering and then anomaly detection. Forgot to add it here. Some caveat, as I said earlier, like all of these information, all of these examples, like we just showed, like 2D, but in reality, they are like many dimensions. It can be even like hundreds of dimensions. And then, and there are like, of course, there are like many other machine learning algorithms. Those are just like the kind of like most common ones and wants to start learning from. And then if anybody wants to learn more about that, which basically how I learned, there's some courses in Coursera. Those are all free courses. So Coursera has some like you can pay if you need a certificate, but you can also just audit the course for free. So you can just choose to audit the course. So there is Andrew Ng, who's actually co-founded Coursera and a really good professor at I think University of California, something like that. So he has this course, machine learning, which is talks mostly about the shallow learning, which is like a course that I think like 10 years old or something, but still really good. And then he did new courses just about deep learning with neural networks and stuff. And this is actually has like they call it specialization or something like that. So there are actually several courses that you can take, not just one. This is the first one of them. And those are I guess you can, like, for learning, there is, I guess you can call, there is a bottom-up approach and then a top-down. So those are mostly bottom-up. You try to understand the basics, and then from there, like, try to get to more and more complicated stuff. Fast AI, it's also a really good course, and they took like the opposite. Like, instead of doing bottom down, you start from top down. Like, since there are like a lot of already libraries and stuff that do most of the work for you, they just tell you, hey, use this library, do that, and then you're gonna have something working magically. And then after you do that and you're happy with it, you start like getting deeper and deeper. Like, how does it work? What, what do you do and stuff like that. Oops. And that's all for me.
Ryan was asking, he's heard good things about the fast.ai course. He was asking, did you complete it? Did you complete the course all the way through?
I actually started but I never completed it. I still need to go and complete it.
So it's a long one. He also shared...
It has different chapters, and you don't have to do the whole thing. You can, I think it's each category, I guess you can call it a category. Each category is maybe like, the course is maybe like a couple hours or something you can watch, and then you can follow with it. But yeah, you don't have to do the whole thing. You can do a portion and then, yeah.
Okay. He mentioned that a friend told him that they just refreshed it, so there might be some new stuff in there. He also shared a link to a near online example of neural networks being used for RL, in which case everyone can play around with it on screen, and provided a link, which I sent to everybody. A question I had for you, you mentioned that like companies like Google and Amazon use artificial neural networks to like crunch numbers. Do they use that sort of thing for like developing advertisements that they send out to their customers?
Definitely, yes.
Okay.
that's how they know a lot about us that sometimes we don't even know about ourselves.
Oh gosh, some of my friends were joking that they got a lot of like therapy ads like deep into isolation quarantine time. And it's like, Google, how did you know? What are some other like examples or applications of machine learning that we might be familiar with?
I mean, there are a lot, and like Andrew Ng, like that's this professor here. He says like well, I guess I forgot machine learning, artificial intelligence is the new electricity. Like, basically, like electricity, like now software, that there is no industry that doesn't use electricity almost. There is no industry that doesn't use some kind of software. In the future, probably is going to be no industry that doesn't use some kind of machine learning. I mean, it goes from, I mean, there's the flashy ones like self-driving cars and stuff like that. There's like, filtering spam emails. There's, like that, like trying to see segmenting markets, like trying to see, you have, you say like you're trying to produce t-shirts, like I want to just produce 3 sizes. What sizes should I produce that will fit most of the people, or something like that. I mean, there's just a lot. Like I can think of specific ones right now, but yeah.
Basically everything.
Yeah.
Well, cool. Does anybody have any questions? Feel free to drop them down in the chat.
Yeah, and I think also there's some interesting stuff in machine learning that like is even now used in like drug discovery and stuff like that. There is a category of machine learning, I forgot what it's called, but basically, like, since like for drug discovery, like you need to like you need to produce something and then test it, and then based on that result, try to refine it, and that takes a lot of time. So first you can have machine learning kind of like predicts what the test can do. But the other thing also that's really interesting is like, since if to do physical tests is very expensive, and even if machine like does the test and you need to and later you have to do it also manually just to verify, you can do sparse number of tests, and then the machine learning will tell you what other tests you can do manually that will give you the most valuable results, so you reduce the amount of physical tests that you have to do. And that will save them a lot of money and speed up the discovery rates. You're muted.
Thank you. There's a question from Kelsey. It's kind of a long one, so I'm going to read it out for you. For refactoring the weights for hidden layers to improve the output, is this something that always moves backwards, output to input, or right to left in those diagrams? Or are there some cases where refactoring the weight makes more sense to adjust on the first few hidden layers closer to the inputs? And how do you know which weight should be adjusted to produce the closest, most reliable output?
So the reason it goes backwards is because like when you are in the middle, you don't know what result is going to give you, right? Like you have to wait until you go all the way to the end and you compare that to, because you're training your model. So you have your result, right? So let's say this is a picture of a cat and you have a cat. When you're in the middle, you don't know whether if it's going to predict a cat or not. So if you wait until you get all the way to the end and tells you whether it's a cat or not, and then once you do that, then you have to go backwards and then start like updating them one by one. I think that's always how it does, and the updates are not like just random. I didn't want to use like a lot of math and stuff like that, but there is like a function that usually is it's a derivative function that makes it's like a ball shape, and then it's called the gradient descent. So you try to make sure you get like the bottom of the ball. That's basically the least error. So you try to make sure if to get all the way to the bottom. If you shoot too far, you're gonna be up there, up again. So you keep changing it until you get to the bottom. That's the lowest error you can get, and that's how it's done, basically.
We have another question from Ryan. He said, when I read about neural networks, often related to supervised learning apps, I bump into the term convolutional. I might be pronouncing that wrong. Neural networks a lot.
Convolutional.
Yes. Convolutional, thank you. Yeah. What does that mean?
So convolution is basically you apply a filter. So what it does, the convolutional neural network is mainly for detecting images. And what it does, because the images have, like each image, if it's just 20 by 20 pixels, which is like really tiny, you have 400 values, right? Because 20 times 20 is 400. So that's a lot of data. And it's kind of basically convolution, it just applies a filter. And it was like, I just want you to get me like the most important pixels in there. And so it makes it kind of like almost smaller and more interested in like the big picture, right? If you're gonna see like a picture of a cat, like the most important stuff, for example, it will be like the area where the eyes and then the ears and then basically what's, the body or something like that, the edges and all that stuff. You don't need, a lot of other information that is there. So yeah, it just applies different filters to reduce the size of the data and make it easier to detect what it is.
So mostly for efficiency.
Yeah.
Okay. Well, I learned a lot today. Does anybody else have any other questions for Yahya before we call it a wrap? I will plan to send out a link to this recording next week to everybody, and I'll also include the slides, if that's all right, Yahya, as well as a link to a few resources that we have both at the library and some of the courses that he recommended. I really appreciate you coming out today to talk to us. Next week, our Tech Talk will be on, I think, digital archiving, so how to name files so you don't lose them. A practice I'm sure we all could be a little better at day to day. But thank you so much for coming today. I hope everybody enjoyed it, and I hope you all have a great weekend.
Thank you.
Thank you.
Thank you. Have a good day, guys.